Bhim section 7.5 Orthogonal Complement. Definition 7.5.1. Suppose I start with an inner product space V and any subset, not necessarily a subspace of V, then I define this set which is called A perp, short form for A perpendicular, which is defined as another subset of V consisting of all those vectors in V which are perpendicular to or orthogonal to all vectors in A. So whatever vector you take here will be perpendicular to whatever vector you take there. That is called A perp. Then it is easy to say that A perp must be a subspace of V. This was any arbitrary subset and this is a subspace. And why is that? Because if I take any two vectors in A perp, in that case I can show that their linear combination will again lie in A perp. So let's just take any x1 and x2 in A perp. Then what I can say is that these two things are orthogonal to anything in A. Now if I take any linear combination of these, say alpha 1 x1 plus alpha 2 x2, then that will also be perpendicular to V, whatever V in A you take, because of the distributivity property of inner product over its first argument. So whatever subset I take, its perp is a subspace. Here is an example. Suppose I take R3 as my vector space and I take this particular vector 1, 1, 0 and say I take another vector which is 1, 0, 0. So my A consists of only these two vectors. I want to find out A perp. So I have to take all vectors that are perpendicular to both these as well as these. As a result, this must be perpendicular to any vector in the xy plane, because if I take any vector in xy plane, it's a linear combination of these two. In other words, my A perp must consist of only the z-axis, all vectors along the z-axis, which is definitely a subspace. So we can say that if I want a vector which is orthogonal to some vectors, it is also orthogonal to any linear combination. So basically A perp is same as if I take span of A and perp of that, they are the same thing. As a result, we generally like to work with only perps of subspaces, because span of anything is a subspace. This motivates definition 7.5.4. If I start S, which is a subspace, not just an arbitrary subset, subspace of V, in that case S perp is given a special name. It is called the orthogonal complement of S in V. Here is an example. Suppose V is R2 and I take S to be this one-dimensional subspace. Remember, in R2 all subspaces are like straight lines passing through the origin or the entire plane or just the point at the origin. So if I take a line like this, then its orthogonal complement is what exactly we expect it to be geometrically. Consider the line which makes 90 degree, so that will be S perp. Similarly, if I say that this is just the origin, so S is the trivial subspace, it is easy to see that S perp will be the entire space. So there the idea of 90 degree is not apparent geometrically, but still the definition holds. And if I work with entire space, so S is equal to V, then its orthogonal complement will be just the trivial subspace. And it is quite easy to see that if I take S perp and perp of that, I will get back to S. Remember, this does not hold for an arbitrary subset of S. It holds for a subspace of S. Theorem 7.5.2 gives us a way to construct an orthogonal complement. You start with some subspace S of V. Now, you start with any O and B of S. In fact, this theorem is perfectly valid even if you work with just an orthogonal basis. So, if you take OGB, that is also perfectly all right. It is not very important that all these things must have unit norm. Now, we know that any orthonormal basis or orthogonal basis for that matter can be extended to a basis of the full space, that was by Gunst-Meillet process. So, I have already had x1 to xk, I put some additional stuff xk plus 1 to xn, which is a basis of V. So, I am tacitly assuming that the dimension of S is k and dimension of V is n. Then, if you consider the space spanned by these red things, this extra part, that will be your S perp. S perp is span of these things. The proof is pretty obvious because if I take any linear combination of these things, then obviously they must be perpendicular to all these things because these red things are all perpendicular to the black things. And conversely, if you take anything which is perpendicular to all these things, it is something in V. So you can express it as a linear combination of all the things. So let's just do the proof in the following way. So I can see 1/2 is very obvious. If I take anything here, that is bound to be perpendicular to all the xi's, as a result orthogonal to S. Now for the other half, I will proceed like this. Suppose I take any V in S perp, which means V is perpendicular to all my vectors in S. Now V is a vector in V and this is a basis, so I can definitely write V is equal to summation alpha I xi and 1 to n. So I want to show that actually all these alphas will be 0 when alpha is 1 to k. So in this thing, these things do not have any contribution. It is made up of only the red parts. And for that, what I shall do is, I shall just find out what alpha i's are. This being an orthogonal or orthonormal basis, I can find that quite easily. So I will do it for orthonormal. Then alpha I is nothing but V inner product xi. And if you are working with orthogonal, you have to also remember to divide by norm of x. Now that is already given to be 0, simply because you know V is perpendicular to S and all these xi's, that is I from 1 to k, they are in S. So in this linear combination, this part has no contribution, so V must come from contribution of only the red parts, which means V must belong to the span of xk to xn, and we have already seen the other part. So that completes the proof. Now we are talking about orthogonal complements. For the time being, let's forget about the orthogonal part and focus on the term complement. We already have the concept of complement of a subspace in a vector space. So let's quickly recall that, and then we will check whether our orthogonal complement, this terminology, is indeed meaningful in the sense that an orthogonal complement is also a complement. Suppose V is a vector space. I said vector space, not necessarily inner product space, not necessarily finite dimensional space, just any vector space. You start with any subspace of V, not a subset, subspace. Then T is called a complement of S in V, where T is another subspace of V, is called a complement of S in V. Sometimes it is called a direct complement. So I will just write the term direct complement of S in V if S plus T is equal to V. That is, every vector in V can be expressed as some vector in S plus some vector in T, and they are as close as possible to being disjoint. Being subspaces, they cannot be fully disjoint because they must contain the null vector. So I say that the intersection is the smallest possible, namely consists of only the null vector. In that case, we call it a direct complement. The term direct complement quickly reminds us that it is not complement in the sense of a set. So it is not same as S complement considering V as the universal set. So let's quickly look at some examples. Suppose we are working in R2, so V is equal to R2 and I take S to be the x-axis. Now I want to come up with some direct complement. One simple direct complement is the y-axis. That is one possible choice. Just observe, if I give you any vector in R2, you can split it up into two parts, one part across S and the other part along T. Also, the two things intersect only at the origin. Now, this is not the only direct complement that S has in R2. For example, here is yet another direct complement. I just take any other line passing through the origin, any other except the x-axis itself. That will also be a direct complement, because if I take any vector here, say anywhere, in that case I can split it up into two parts, one part lying in S and the other part lying in T, just by the parallelogram law. And here again, the intersection of these two subspaces, this subspace and this subspace, is just the origin. So you can see this direct complement idea is basically the concept of independence, not being along the same line and spanning the space, but in terms of subspaces. So I can say S and T are linearly independent subspaces that generates the entire space V. We do not use these terms because they are not vectors, but they are subspaces. That is direct complement. And here we do not assume that this has to be inner product space or it is finite dimensional space. Now, when we are working over an inner product space and we are talking about orthonormal basis, Gram-Schmidt orthogonalization, we typically work with a finite dimensional space. Then we have the concept of an orthogonal complement. So the natural question is, we have used the term complement in two places, orthogonal complement and just complement. Are they related? And the natural thing, based on just English usage, is that an orthogonal complement should better be a complement. Something like, if you have a black box should also be a box. That's not always true. A pineapple is not an apple, but let's see what happens in this case. The answer is provided by theorem 7.5.3. Here V is an inner product space. We are specializing to inner product space. You start with any subspace of V, then S perp, the orthogonal complement, is indeed a direct complement of S in V. The theorem has some other parts also, but first let's prove this. So to prove this, I have to show that S plus S perp, that should make up entire V. And that is pretty straightforward, because if I take anything here, that is anything in S and anything in S perp, add them up, both of them are lying inside V, so their sum should again be inside V. So this half is just obvious. Now in order to prove the other half, that is to show that anything in V can be written in this way, the technique is pretty simple, using the idea of extension of an orthonormal basis. What I do is I start with an orthonormal basis of S, call it x1 to xk, that's an orthonormal basis of S. And you extend it to an orthonormal basis of entire V. So you get an orthonormal basis of S perp also from just the extension. So I extend it to some x1 to xk followed by the red part, and the entire thing is orthonormal basis of V. Then we know that this red part forms an orthonormal basis of S part. Okay, so now you start with any vector v in V. Then, since this is an orthonormal basis of V, you can express V as a linear combination of all these things. So it is something like alpha 1 times x1, alpha k times xk, followed by some alpha k plus 1 times this, alpha n times this. Well, so split it up like this. The part which we are using here, that is alpha 1 x1 to alpha k xk, that part is in S. And the part that you have been here, that part is in S pop. So I have split up any vector in V into two parts. One is in S and the other in S pop. So that condition is satisfied. The next condition that I have to check is whether their intersection is only the null vector. Okay, so suppose I take any vector in S intersection S pop. Now what is S pop? S pop consists of all those vectors which are perpendicular to every vector in S. So if X is in this set, X has got to be perpendicular to itself because it is in S pop and it is also in S. So it must be perpendicular to itself, which necessarily forces that X inner product with itself must be equal to 0, and that is possible if and only if X is itself the 0 vector, because that is one of the conditions of inner product. So we can see that the term orthogonal complement is indeed justified. It is a complement. The second part is absolutely simple. In fact, it is a property of direct complements. So if you have dimension of V and from that you subtract dimension of S, immediately you get dimension of S pop, which is pretty obvious because that's how I constructed it. I took a basis of this and I extended it to a basis of V. Whatever was the extra part, the number of them is clearly dimension of V minus dimension of S, that constituted a basis, an orthonormal basis of S pop. So clearly this thing must hold. This is in fact true about any direct complement, not just orthogonal complement. However, there is one beauty about orthogonal complement which was not present for direct complement. Direct complement was not unique, but orthogonal complement is unique. And it is this thing which gives us this powerful result, something that I have already mentioned. S perp of perp is again S itself. Of course, to prove this, you do not need all this machinery. It is just straightforward argument following from the fact that if X is perpendicular to Y, then Y is perpendicular to X, comes from the fact that X inner product Y is same as Y inner product X, possibly with a complex conjugation. So this is a very straightforward result. You really do not need to put it in this list. Unfortunately, Rao Bhima Shankaram being Rao Bhima Shankaram, they specialize in just mixing odd things together, so they have put this as part of this theorem. Yes, you can obtain this from this also, but that is not important. Now, just a point that this result does not hold for any arbitrary direct complement. Here is a little counter example. Suppose I work with R2 and my S is the x-axis. I take any direct complement, and I have already told you this line will be one direct complement. I want to take one direct complement of T. Well, I just take any other line. I can take this line, U, and that will be another direct complement. So here I have S. A complement of that is T. A complement of T is U, and U is not same as S. So this property does not hold for general direct complements, but it holds for orthogonal complements. So you should understand that these two things have completely different status. This is actually true for any direct complement, and this holds only for orthogonal complement. So this theorem is a very typical Rao Bhima Shankaram theorem, putting unrelated things together to confuse the student.